Well, hello again. Welcome to Chemistry A, Unit 3, Quantum Mechanics and Intro to Bonding, Day 1. Let's get started. The modern theory of electrons in atoms is called the quantum mechanical model. This is a mathematical model. Now, the two models that we've discussed so far include the Bohr model, which is the model that talks about the electrons that orbit around the nucleus in a fixed path, and it resembles the planets orbiting around the sun. And we know from our earlier discussions that that is not a correct model. The more correct model is the quantum mechanical model, or also known as the electron cloud model. This model was based on mathematical probability of finding electrons in their orbitals, and this is the current one that we use today. It has some common things like the Bohr model does, and one of those is that it does restrict the energy of electrons to certain values. In other words, an electron is stuck in a certain energy level, just like in the Bohr model. The quantum mechanical model is the same as well. But unlike Bohr, the electrons do not move in exact paths around the nucleus. As I've told you before, they move in random directions around the nucleus. And that is one of the reasons why we cannot use where the electrons are as the edge of an atom when we do atomic radius. The quantum mechanical model has atomic orbitals in them. These are often thought of as a region of space in which there is a high chance of finding an electron or a high probability of finding the electron. Okay? Just because what that means is the electrons are not necessarily always going to be there, but if you were able to find them, that is a good chance of where you would find them. Now, each atom has principal quantum numbers, which are the energy levels. Within each energy level, there may be several orbitals with different shapes and at a different energy level, called energy sublevels. Each energy sublevel corresponds to a different shape where they are found. For example, if you open to page 131, figure 5.5, that will help you to understand this component. Now, on 131, you'll notice that those shapes are outlined there. You have the S's and the P's, and the S is like a sphere, and the P's look like dumbbells, and etc., etc. We talked about that in the periodic table unit as well. The way in which the electrons are arranged in various orbits around the nuclei are called electron configurations. This is kind of what we've talked about already with 1s2, 2s2, 2p2, etc., like we had in our periodic table unit, along with our reading guide so far, as well as the internet project. Now, there were three rules that we stated for electron configurations. Rule number 1 is the off-ball principle. Electrons will occupy the lowest orbitals first. Each box or dash represents an atomic orbital. So it will fill from the lowest energy level, 1s, to the 2s level, to the 2p level, to the 3s level, to the 3p level, to the 4s level, then to the 3d level. So the 3d energy level is actually more powerful than the 4s. Okay? Here's another way of looking at it. How the electrons will fill as you move left to right and down in the periodic table. So we have 1s, 2s, 2p, 3s, and as you can see, there are more orbitals and there are more energy levels. And as you can see, they fill from the lowest energy level to the highest energy level. Okay. Number 2 is the Pauli exclusion principle. This is rule number 2 of how the electrons fill their orbits. This states that an atomic orbital may describe at most 2 electrons, and the spins must be opposite to occupy the same orbit. And this is shown by 2 little arrows in the boxes. And the third rule is the Pauli exclusion principle. Okay? And here's some examples of this. All right. And what happens here is that the electrons will fill each energy level first. So here's what takes place. All right. And it happens in the two p orbitals first. The first electron will go into the 2p orbital, and then the next electron will go with the same spin in the next available orbital, and then the next available orbital will get the other spin, and then eventually what will happen is they will pair up into each orbital. Okay? That was Pauli's exclusion principle. And those are some examples of the two orbitals and all that. And now Hund's rule, I misspoke. Hund's rule is the rule where electrons will occupy orbitals of the same energy in a way that makes the number of orbitals biggest. Okay? Electrons enter each orbital until all are filled in one direction and then pair up with opposite spins. And that is what you can see up here at the top in the Pauli exclusion examples. Each box will receive an electron before it will receive a couple or a second one. Okay. So here, as you can see with nitrogen, we have 1s2, 2s2, and then in the 2p we have a nitrogen that has its 3 shells maximum filled in one direction. And then if we were to go from nitrogen to the next element, the next electron would go right here in this box with nitrogen, the first 2p box. And the spin would be down just like in the 1s boxes. Okay?